Hello everyone, my name is PAFastrack and I am a master's student in SAP's Computing Science. I'm going to present our paper submitted to CDC 2021, which proposes a safe path planning method called PAFastrack, which is a modification of the work previously done by Sylvia Herbert Mochen and their colleagues called PAFastrack, which I'm going to reference in later slides. A path planning method, which is to be used in real time, needs to be computationally efficient and fast. But for a planner to be fast, it needs to ignore some dynamical complexities and constraints of the system, which is following the planned path, in order to decrease computation time. This will result in a tracking error, of course, and a tracking error can be hazardous in presence of obstacles because the planned path may avoid the obstacles, but the agent wouldn't be able to follow the path perfectly. One way to make sure the planned path is safe despite the imperfect tracking is to account for a tracking error bound or TEB when checking for paths collision with obstacles. And PAFastrack does exactly that, albeit a bit too conservatively, which we'll talk about in detail. PAFastrack assumes the robot consists of two separate agents, a tracking system which represents the robot's dynamics with all its complexities and constraints, the state of which is represented by S and through this dynamical equation here. And also a planning system, which is a simple lower dimensional dynamical system of the form in here, which can follow perfectly the path generated by the real-time planning algorithm. PAFastrack then assumes that the tracking system is trying to follow the planning system and decrease the distance. The problem of TB computation then comes down to calculating the maximum distance between these two agents, which PAFastrack does, by formulating it as a zero-sum pursuit evasion differential game in which the planning system is actively trying to avoid the tracking system. And of course, disturbances have an adverse effect too. The relative state is calculated through an equation like this one here, in which Q is a matrix that matches the common states of S and P, and phi is a transform of an identity, but possibly a rotation matrix. The authors in PAFastrack then go ahead and form a cost function, which is a measure of the distance between the two agents and is a function of time and relative position, and is shown by L here. The value function would then be defined as the equation here. Please notice that the value function yields the maximum value of the cost through time when the tracking system's control input is trying to minimize the cost and disturbance, and planning system's control input are trying to maximize it. The value and from that, the TB can then be obtained by solving an HJ variational inequality. For more details on HJ variational inequality, pursuit evasion games, and the exact computation of TEB, please refer to the references listed here. PAFastrack manages to compute a very safe tracking error bound, which can then be used with any fast online planning algorithm at the time of collision check to provide a safe path. And the good news is the HJ heavy computation can all be done offline, but there is something too conservative about PAFastrack, and that is the assumption of planning system actively trying to avoid the tracking system, which brings us to our proposed algorithm. We are going to keep the assumption of two separate agents, but instead of assuming worst behavior for the planning system, we assume it follows some motion primitives, for example. We know for a fact that many fast online planning algorithms, particularly sample-based ones, use straight lines to form a path. So the assumption of a planning system always following a straight line is actually very probable. Now, I am going to explain the TB computation for each linear segment first and then combine them for the whole path. But before that, in order to better explain the theory, as in the paper, we are going to use an example. Assume the robot is actually a 5D extended Dubin's car, as in this equation. SU represents both the robot and tracking system's state. Now, let's assume we are going to use an RT algorithm for planning, which requires a point mass planning system dynamics. And let's assume the planning system's velocity is also constant. So the angle of the planning system is its input. With these two equations as tracking system and planning system, we can write the equation for relative state as in the form down here. And all these equations are, of course, represented with respect to some fixed coordinate frame. So what if we assume the equations in the previous slide are actually represented with respect to a frame which is fixed in position but has an x-axis lying in the direction of the path segment, like in this figure? With that assumption, since the planning system is always moving along the path, its equation reduces to p dot equals x dot equals v hat. And the relative state equation changes to this one here. Notice that there is no planning control input anymore. And we replace that with a known behavior, which is following a straight line. Now, this is what happens to the value function with the new relative state. Since the cost is a function of relative state and R doesn't depend on a planning control input, this maximization here can be omitted, and the value function reduces to this form here, which is the maximum with respect to D of the minimum with respect to tracking systems control input of the maximum with respect to time of the loss. After solving the inequality for the value function, we get the figure in this slide. On the right, you can see a 3D plot of the value function for each relative x and y when relative theta equals 0, relative velocity equals 1.6, and linear velocity equals 1.6, and angular velocity equals minus 2.1. On the left, you can see the contour map of the same function at the same slice. In FastTrack, it is proven that if you start at a relative position that lies inside a level set, which are these solid lines, colored solid lines here, you will always remain inside that certain level set if you use the optimal control, of course. And each level has a certain value, and from that, a certain TB can be calculated. And since we assume the orientation of the frame and matching those of the path, any value function we compute and form for a segment is in fact the same for any other segment with any direction, as long as the planning system stays on a straight line. And having the relative state at the beginning of linear segment, we can easily get the TB from the value function or lookup table computed beforehand. The only times the planning system is not moving on a straight line is at the intersection of segments. So let's imagine we have two consecutive segments which have a relative angle theta 1, 2. We have the value function for the first segment, and this figure is a schematic of the contour map, for example. We know that this is also the value function for the second segment as long as the frame orientation is set properly. And from first segment's orientation to the next, we just need a rotation of theta 1, 2 in the frame as depicted in this figure. Now, if we are at the red point in the first figure at the end of the first linear segment, when the direction changes, the level set will rotate, but our relative position is still the same point, which reads different values in the new coordinate frame and maybe in a different level set. So we may experience a jump in the value and hence the TP at the intersection of segments. If we know exactly where we are at the end of the line, we can directly read the new TB value for the second segment, which may not be different from the first segment actually. But since we need the TB for the whole path at the time of online planning, we need to assume the worst case, but our method is still going to be much less conservative than FastTrack, since FastTrack assumes the worst case at every given instance of time, but we only assume that at the intersections. So to summarize, this is what we suggest. We are going to have a sequence of TBs which correspond to each linear segment of the path since we are planning in an unknown environment. The online planner will be called several times for replanning when new information is available or the previous path is unsafe and so on. Every time the planner is called, the list of TBs is exactly and easily extractable for the path to be planned. And this is how the list of TBs are actually calculated. We have an initial relative position, the TB, and the level set for that relative state can be extracted. Let's assume it's red level set here. So then we assume the worst jump any point in this level can have, and we read the value of the level set that contains the previous level set after any rotation, which in this figure seems to be the last one here. This will give us the TB for the next segment, and we continue the same procedure for the following segments. The online planner is then modified slightly to work with a list of TBs instead of just one. And this process of having a list instead of just one value makes actually perfect sense if you think about it, because the more uncertain about the future we are, the more cautious we need to be. So here's a modification to an online planning algorithm as suggested in the paper. As you can see, while the goal is not reached, the algorithm generates a random point, finds its nearest neighbor and its depth in the tree. Based on the depth, it should choose a TB from the list, and with the chosen TB, the path from the nearest neighbor to the point is checked for collision, and if safe, the point is added to the tree. The algorithm has been tested on two different dynamical systems. The first has a 5D extended Dubin's car tracking system and a 2D point mass planner. On the left, you can see the tracked position of the robot. The blue dashed lines are the planned path, and the blue bands are the TBs used at the time of planning. The obstacles are unknown at the beginning, and every lighter red parts of the obstacles are the sensed part, actually. When new information is available that makes the previous path unsafe, the algorithm replans a new path. And on the top right here, you can see a slice of the value function for both original and PAFastrack methods in red and green, respectively. From these two figures, the lower value of the TB in our method can be observed easily. This figure here shows the TEB from the original FastTrack in red, the first TB in our list in green, and the actual tracking error in blue. The jumps here correspond to segment changes, and you can see that our method provides a very tight error bound indeed. You can see the same outcomes in the second system, which has a 4D double integrator tracking dynamics and a 2D point mass planning system. Thanks for your attention. I would be happy to answer any questions.